Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this session. In the previous session, we looked at how to calculate the noise at the output of the PLL. So, today in this session, we will look at the noise optimization with respect to bandwidth of the PLL. So, before I start with the noise optimization, let us just have a quick recap of the noise in the PLL. So, I will just draw the small signal block diagram for the different noise sources which we have seen earlier. So, you have here you have phi reference, then the noise gets added up for the reference, right, and you feed back at the input. You have PFT plus charge pump. So, I have treated PFT noise separate and charge pump noise separate. You can use that, take it together also. So, this is SPFT, and then you have charge pump whose output is current. So, the noise which is added at the output of the charge pump, that is current noise actually. So, this is S charge pump. These are S is referring to the noise spectral density. Then you have the resistor with a noise source V and R and noise spectral density S of R. So, let me just write noise spectral density as S of R, followed by a capacitor C1, and then you have capacitor C2. This is R, followed by VCO with gain K VCO over S. The noise added by the VCO is in terms of phase, which is phi VCO, and this is V control voltage node, and you get it, feed this signal back to the divider, frequency divider. So, you have the divide by N here, you add the noise at the output of the divider in terms of phase, and this feeds back. So, this was the small signal model of the noise in the PLL, and we were analyzing this noise with the noise transfer functions for the PLL. So, let us just bring the plot where we were looking at the output noise spectral density with respect to the input noise spectral density. Okay. So, this is the noise plot which we were looking at the output of the PLL. So, what we are plotting here is, just to recall, S R phi out is nothing but this is SR times NTF of noise transfer function for the resistors, where NTF of R is equal to phi out divided by VR. This is VR, your equivalent noise voltage for the resistor. So, we are plotting the output noise spectral densities. The important thing which we would like to highlight is the following, that your reference noise phi out R, your charge pump noise is actually low pass filtered. So, reference noise, reference and charge pump noise is low pass filtered. Okay. Why do I say low pass filtered? Well, you see the transfer function which we are having is flat from DC and then it drops. So, this is low pass filtering, okay, is low pass filtered. Second, you look at the VCO noise. So, the VCO noise is actually high pass filtered, and if you look at it, it is like this. And what you are seeing at the higher frequency is because of the noise profile itself. So, VCO noise is high pass filtered, okay. And then you have resistance noise. Resistance input noise for the resistance is actually flat, and the output noise what you see is lower at the higher is low value at lower frequency and low value at the higher frequency, and in between it peaks. So, the resistor noise is band pass filter. So, now you think about it, if I have multiple noise sources in the system and all the noise sources, they are not filtered by the same filter. It is like if all the noise sources were getting filtered by a low pass filter, okay, then we can very well say that it is better to choose a lower bandwidth for the low pass filter to minimize the output noise. Similarly, if all the noise sources in the PLL block, they were filtered by high pass filter, then it would be better that we choose a larger bandwidth for the high pass filter, so that we filter out the output noise. Now, here there are some noise sources which are low pass filters, some noise sources which are high pass filtered. So, without calculating or without finding either by simulation or by calculation the noise for a given bandwidth, you cannot say whether that particular bandwidth which you are choosing is optimizing the noise or not. Okay. So, for that particular reason, what you need to do is the following. You start, so the noise optimization procedure starts like this. So, let me just write it. This is noise optimization procedure. So, first you, to begin with, you choose some bandwidth, choose unity gain bandwidth which you would like for the PLL, okay, omega u, and let us say that phase margin which you want is decided by transient settling. So, that is already a number which you have picked. You need to find which is the optimum omega u. Phase margin is decided by transient settling, okay, and that is already given. You can assume that either given or you have already chosen. So, phase margin is fixed in the optimization, during the optimization. Okay. So, when I pick up omega u, so for given omega u and phi m, find loop components. Okay. With the same procedure which we saw earlier, that the phase plot at the unity gain frequency should be maximally flat, that is derivative of phase is equal to 0. So, using that we will find the loop components. Now, when we find the loop components, few things we have assumed or we chose, okay, and few things will be given for the design. So, what will be given for the design? KVCO for the oscillator is fixed, okay. KVCO for the oscillator is fixed. So, when you, this whole optimization procedure is at system level and circuit level iteratively, okay. So, we design an oscillator, we find the oscillator phase noise, independent oscillator phase noise and the KVCO for the oscillator. So, KVCO is fixed. You have to choose R in these calculations, right, because we have seen that for the loop gain and the phase margin as we want, you have to make a choice on R. Only when you choose R and KVCO is given, then only you will find C1, C2 and ICP, such that you get the chosen omega u and phase margin for the loop components, and you know that the resistor is a noisy block. So, once you make a choice on R and you find that the overall noise it does not meet your requirements, then you have to go back and change for R. So, let us say we chose R here, we calculate C1, C2 and ICP. Once your C1, C2 and ICP are found out, then what you are going to do, calculate noise transfer functions for all the noise sources, calculate noise transfer functions for all noise sources, okay, and you find noise of all sources independently. Sources find or find either, here there are two options, either you calculate or you simulate. Okay. So, you can do both the things, we will see what we are going to do, but whichever way it is, you calculate or simulate noise of all sources independently. Okay. So, what we are doing, when we are saying we calculate or simulate noise of all sources independently, we are actually calculating or we are finding S of R, S of 5 VCO, right, S of or these are the noise power spectral densities, S of PFT, S of charge pump, S of divider and so on. Okay. These have to be found out. Once you know the noise and the NTFs, you know that the total output noise you can calculate, which is S out total, right. You add up all these things multiplied by their noise transfer function. So, I will write S I, where I denotes the ith source, times NTF of I, noise transfer function for the ith noise source whole square. Okay, whatever the noise components, you find this out and you calculate then the jitter given by 2 by T by 2 pi, T is the output clock period into summation of S out total df, okay, and frequency goes from 0 to infinity or 0 to f ref by 2 in our calculations, okay, because it is a sample system. So, most of the time our simulations are going to be valid till f ref by 2 or our modeling is going to be valid till f ref by 2. So, this is S out total. So, now you started with one particular omega u and phase margin, and what you got is the jitter value. Okay. So, you pick that jitter and you plot it. So, I am going to plot jitter versus omega u. So, I picked one particular frequency omega u, right, and I got a certain value of jitter. You need to repeat this exercise, repeat steps 2 to 5, okay, for different omega u. Now, this depends on what omega u you prefer or which is going to give you noise optimization omega u. So, you keep normally you can vary from just, this is just an example, you can vary from omega ref by 10 because till that point our modeling is valid, and maybe you can go omega ref by 100 or 1000, that depends. So, all these things we are doing at system level. So, you keep on doing this, okay, omega ref by 10 to omega ref by 100. So, let us say I pick up one value, this is omega ref by 100, right. So, when I am going to find, and I am repeating this exercise, each of these frequencies is giving me, unity gain frequency is going to give me some amount of jitter. What you are going to find that this particular plot may look like this. It can be any thing. So, it's the only thing is it may have some peak point or it may not have that optimum point. So, the way I have shown you the plot, you see that there exists a point where the noise is optimum. So, in this particular case, as soon as we chose KVCO and the phase noise of the oscillator, the power consumption in the oscillator is fixed. Okay. We got a certain ICP, the power consumption in the charge pump is also fixed, and you are designing it for a PLL where your reference frequency and output frequencies are fixed. So, the power consumption in all other blocks are also fixed. The only thing which we are, when we vary omega u, okay, when we vary omega u without making any changes to the reference or the output frequency, the only other block in which the power consumption will vary is ICP varies, and which in turn actually vary power consumption in charge pump. Okay. So, only that power consumption will vary, rest all will remain same. So, when we do this, right, we find certain omega opt. Now, the question arises whether the value of the jitter which you have, let us say sigma opt 1, whether this sigma opt 1 is lesser than your jitter requirements, okay, or it is larger than the jitter requirements. So, depending on what we have, so let us say case 1 where sigma opt 1 is greater than sigma desired from the PLL. Okay, it can happen because without calculating everything you do not know what jitter value you are going to have. So, if sigma opt 1 is greater than sigma desired, then for the desired jitter value you have to reduce the noise of components. Okay. Now, if let us say sigma opt 1 is equal to sigma desired, then you can say equal or within the range very close, that okay, you can say that yeah, this is fine within the tolerable limits. You can go ahead and just confirm the values of C1, C2 and ICP at omega opt, and your PLL design at system level is over. You can just now plug in the components and your PLL should work. But in case when sigma opt 1 is greater than sigma desired, it is beyond the margin of error which you can tolerate at for the desired output frequency, then what you have to do is you have to go back and reduce the noise of the sources. Okay. If this happens, you have to reduce noise of different sources. Now, how will you reduce the noise of different sources? That is the question. Now, this PFD charge pump, PFD is working at the fixed reference rate, right. It is normally one thing is the noise contribution by the PFD is normally very less, but it works at the fixed reference rate. You will not change the noise by designing it again. The only way it can be that okay, you increase the sizes of transistor, you consume more current there. But before we take a call that which particular component or which particular noise is dominating, do one thing here. Okay, find noise contributions of each source to the output. Noise contribution, I am looking for sigma contribution, which particular component contributes more to the output. So, what we have found earlier is sigma total. Okay. What I am asking you to do is the following: you find sigma out due to resistor. So, if I just call this sigma out due to R, this is going to be a square root of, just an example, S of R times NTF of R whole square df 0 to ref by 2, right, into T by 2 pi. So, this is the jitter contribution by the resistor to the output. Similarly, I am going to find for all the components sigma VCO to the output, sigma R to the output there, sigma charge pump to the output, right. So, you find for all these components, charge pump, PFD, right, reference and sigma of divider. Okay. And where I am going to find for what omega u, all these contributions I am going to find for omega opt, because that is the minimum jitter which I have in the system, okay, after choosing the noise from independent sources. So, I need to find out which of these components actually is contributing most. Okay. See, if you want to reduce the noise of any component, then you should know that whether that noise is dominant or not. If it turns out that, let us say, the resistor noise is dominating, because we chose the value of resistor randomly to begin with, just you start designing, so 1K, 2K, whatever you would like, you can choose that. And if it happens that the resistor noise is dominating, if you choose a large value of the resistor noise is going to dominate. If resistor noise dominates, then there is no point in addressing the noise in the VCO. Okay. So, we are going to find all these jitter contributions independently at omega u equal to omega opt 1. Okay. So, what we are going to do is, once we find that, then we should look for these. If your sigma R at the output dominates other noise sources, right, then reduce R and redo steps 2 to 5 earlier, reduce R and repeat steps 2 to 5 in the procedure. Okay. Here it was 2 to 4, by the way, 2 to 5 in our procedure. So, what it is going to do is, if your resistor noise has dominated the output noise, and you go ahead and you choose a different value of R, that means you are going to get different value of C1 and C2 and ICP, you again go and plot the curve. It may happen that because you reduce the value of the resistor, so resistor noise reduces. So, maybe you get something kind of this, quite possible. Okay. What bandwidth? It again depends. So, you get another value, okay, which is sigma opt 2, I can call this sigma opt 2, and at different frequency, which is omega opt 2. So, the coordinates will be omega opt 2 and sigma opt 2. If it meets your requirements, well and good. If it does not meet your requirement, it is like this. If it meets your requirements, it is below what you require, then you can think you can increase the resistor value, okay, and you may still be able to meet the requirements. If it is above, if sigma opt 2 is still greater than sigma desired, then you go ahead again and reduce the value of the resistor more and find the noise, okay, find the output noise. So, this is with respect to the resistor. Now, the question you can always ask is that okay, if the resistor noise is so important, right, it can dominate at any point of time, then why do not I use a low value of the resistor itself, okay, so that I make it noiseless. There is a trade off between the value of the resistor and your area for the capacitor C1. So, we have seen earlier that omega z in the loop gain expression is R C1, okay, and omega u square is omega z times omega P3, okay, and all these values we calculated, and it turns out to be that if for the desired phase margin, right, you have a fixed C1 by C2 and you have a relationship between omega u and omega z in terms of C1 by C2, which is that is independent of R. So, as soon as we get omega z and we need to find the exact value of C1, the value of R matters. So, here C1 is omega z times R. So, what I am trying to tell you here is that for given omega u and phase margin, your omega z is fixed. Okay. So, if omega z is fixed and you reduce the value of R, the value of C1 will go up. And if the value of C1 goes up, then what happens is if R reduces, C1 will increase and area occupied by C1 will increase, which is a problem, okay, which is a problem. Problem in the sense how much area you are going to occupy on chip. An IC is like a real estate, you keep on increasing the area, your cost will keep on increasing. Okay. So, there is a limit, we cannot just always start with the lower value of resistor to make it noise non-dominant, or it is like should be always not noticeable. Well, there is a limit because of the area which we can afford for C1. So, if your resistor noise dominates, you can keep on changing the resistor value to a lower value iteratively, such that you meet your requirements and you do not sacrifice the area more than required for the capture value, capture C1. Okay. So, this is one case. Now, the case which we have discussed is only with respect to R. Now, if you find that, let us say another options, because you can have multiple options here. If sigma out VCO dominates, what to do? Dominates output noise and you still do not meet the requirements. In that case, well, the plot which I showed you earlier, in this case actually VCO noise dominates, right. So, if VCO noise dominates, then the only option which you have is, because you cannot change the reference frequency, you cannot change the output frequency, because that is reference is fixed, output frequency is something which you want, and at omega OPT and your sigma OPT it does not meet your requirement, then the only way is, if this happens, increase power consumption in VCO and reduce its output noise. That is the only way. Okay. This is well given that the oscillator which you are using is one of the best designed oscillators. It is not a lousy oscillator which you still have margin for improvement of noise. So, to begin with we designed the oscillator which is good, and the only way to reduce the output noise of the oscillator will then what you will see is the only way is you have to reduce increase the power consumption and reduce the noise. So, you do that and you get the phase noise of the oscillator, you go back again to your jitter versus sigma plot, again do it, you may find that you meet your requirements. If you meet the requirements, well and good. If you do not meet your requirements, then you have to again increase the power consumption in the oscillator and reduce the output noise. Okay. So, that is something which we need to do when VCO noise dominates. Now, in this case I will tell you one trick which is often used. So, let us say you have a VCO block and it gives you some output noise, okay, phase noise, which is something which we have been talking about. So, if I want to reduce the VCO noise, one of the easiest way is that you take two copies of such oscillator, okay, and connect them node to node. Okay, connect them node to node means each component of the original design in the oscillator is doubled. Okay. So, if you do that, then what happens is you can think that each of these oscillators were oscillating independently earlier at the desired frequency and they will have the same noise. So, if I club them together, the oscillation frequency will not change, okay. The power consumption will double and the phase noise will reduce by 3 dB. We will see the noise in the relationship between the noise in the oscillator and the power consumption later, but this is in general true that you double the power consumption, your phase noise improves by 3 dB. Okay. So, this will help in reducing VCO's phase noise. Okay. So, I will do this if VCO's noise dominates and then I can again calculate the jitter versus sigma plot, and if it is within the limits, good, if it is not, then I have to redo it. Then the next case is, let us say if your charge pump output noise dominates, what to do? If charge pump output noise dominates, then the only option which you or the options which you have before you is that you increase the charge pump current. But if you increase the charge pump current itself, right, then your unity gain bandwidth and everything will be different. So, in that case what you do is, if charge pump noise dominates, then you first reduce R, this will increase charge pump current. Okay, this will increase ICP, and if it increases ICP, charge pump noise will reduce. Okay. So, well, as you reduce R, you have to recalculate all C1, C2 and everything. The charge pump current is surely going to be larger and the charge pump noise will be lesser. So, based on which noise is dominating your output noise, if you are not meeting the requirements, you can target that and you get the new jitter versus bandwidth plot such that you meet all the requirement. So, finally, you may have for example, if I do all such stuff, it may turn out that I get a plot something like this, and this is the optimum bandwidth which I can pick. Whichever is the optimum bandwidth for the desired jitter, you go and pick that particular value, okay, and then you will find all components are C1, C2, ICP. You plug in these components in your circuit design and hopefully the magic will happen and it will work. Okay. Now, the cases which we have listed here is when your jitter is more than the desired. Now, case 2 is when your sigma opt 1 is actually less than your sigma desired. So, what would you like to do? Would you like to just say, okay, I need let us say 2 picosecond of RMS jitter, I am getting 500 femtosecond of RMS jitter, well, it is within the margin. So, I would not do anything. Well, that will not be a good option, because it is a trade off in the design. If your jitter is lower, then by default you can think about it that your power consumption in the design is larger. Okay. So, it is like I need 2 picoseconds, I am getting 500 picoseconds, right. So, I am spending power for 500 femtosecond, but my requirement is not 500 femtosecond, it is only 2 picosecond. So, if I try to get 2 picosecond of jitter, then I can reduce my power consumption. Okay. So, in that way you can go ahead and find out the way we have found that okay, sigma, VCO and all those things, you find here that which of these noise sources is least dominant. Okay. So, reference is coming from outside, you have divider, you have your PFT, charge pump and so on. So, once you find which is least dominant, mostly it will be either your R or VCO or charge pump plus PFT. So, you find which one is least dominant, and based on that you reduce the power consumption in the design. Okay. So, let us say if resistor noise is least dominant, if R noise is least dominant, then in that particular case what you do is you increase R. Increase R. If you increase R, what will happen is your ICP will reduce. Your ICP will reduce, your C1 will also reduce by the way, and if by reducing ICP your power consumption will actually reduce in the PLL, and you can approach the sigma desired. Okay. You are actually increasing noise at the expense of lesser power consumption. So, a power optimized design for the desired jitter value, you have to do this iteratively till the time you meet your jitter requirements with the minimum amount of power consumption. Okay. So, when it is lesser you do this, when it is greater we have discussed the steps. Finally, before you decide on unity gain bandwidth and your jitter, you should check with these plots such that you get the best possible design for the PLL. Okay. Now, an important part here is regarding the phase margin, though I have not, I told that comes from the transient simulations. If you do not have any requirement from the transient simulation, it is better to keep the phase margin above 60 degree across process corners, right. Then you will see, okay, I will start with phase margin of let us say 70 degree. So, if you start with phase margin of 70 degree, your C1 will be quite large. So, if it depends on application, I will just write if there is no requirement from the application side on phase margin, requirement on phase margin from application side, okay, choose phase margin. Typically this is just a rule of thumb which I am applying here, phase margin greater than 60 degree, okay, and then design your PLL. Okay. Now, greater than 60, you can say between 60 to 90 there is a lot of range. Well, 60 to 90 there is a lot of range, but there will be some variation in phase margin across process corner. Okay, so make sure it is greater than 60 degree across process corner, and then you will also see that based on the phase margin, the noise contribution also change bit. The ratio of C1 by C2 will vary based on the phase margin, which will change the noise transfer functions. So, you can calculate that. Okay. So, once I know my other noise sources, I can make phase margin also as a variable if there are no requirements, maybe between 60 to 75 degree, and see which is giving me a better output noise. Okay. So, there will always be a trade off. If you want a larger phase margin, your capture area will be large. Okay. So, that is something which you need to always keep in mind, right. Okay. Thank you.